And we can hear the wind. Good. Live stream is running. Let me check. Okay, audio seems okay. Good. So. Right, I hope there's no specific reason for a drop in attendance from last week. I think we'll get started, and in case people need to catch up, there's recordings. We started a new unit last time, just touching the first few bits, and we'll dig into this a bit more today. That was on parallel algorithms, and we've already had a quick look at the main model of computation that we'll use for this unit. And I commented a bit on the gap between theory and practice on this. Unfortunately, it's quite tricky to program parallel algorithms in practice at this point still. You have to pay attention to many things, and if you want the implementation to be fast, even more so. So what we'll try to focus on in the module is the algorithmic principles behind it, and hiding some of the technicalities that you still have to deal with. I think it's to a degree a question of time. The software frameworks have become more convenient to use, and they handle some of the performance issues automatically. And for specifically the first type of problems that we'll look at, it works at a nice level of abstraction already. But we'll come back to that. That's just for framing the discussion mostly. What we'll study is the PRAM model, and this is all repetition. We've gone through this last time in more detail. So we're in the shared memory world. It's one big computer, and communication is via writing to specific memory cells. That is indeed what almost all computers today are. They are multi-core, but shared memory parallel computers. The formal model is that we have essentially several random access machines in the style that we've defined them in Unit 1, but they share one long piece of memory, and they run in parallel and in lockstep. So there's a shared clock, which I tried to draw here. So each of those machines does one instruction at each step at each time step, and there's no synchronization needed between them because they share a clock, so they run at this exactly same speed. And communication is only by reading and writing to main memory, and they can have your algorithm can invent some convention. Say the first memory cell is a signal that everyone's ready, or something like that. We'll see more examples. We already talked about this as well. If I have multiple cores that may read and write the same memory cell, I have to think about what that means. And basically for writes, we have to worry about what happens if several people try to write at the same time to the same memory location. Different options will mostly focus on this, but you'll do a little bit in the tutorials, some exercises with the other models as well. So mostly we assume we can concurrently read a point because there's not much of a conflict happening if you just read the same location. But writing to the same location is forbidden. Only one processing element at a time is allowed to write at the same place. So that will be the usual model that reflects hardware best. But the others also exist and have some interesting properties. And that's basically where we stopped last time. We looked at the execution costs. And it is a bit more refined a picture here. We don't just have running time. We have time or span and work, which we'll have to worry about separately. Where we left off last time is at this point, we defined the running time of a PRAM program, a parallel algorithm, as consisting of these two parts, span and work. Span is the overall number of time steps until all the processing elements finish, but they can do this in parallel, whereas work is the overall number of instructions summed up over all the processing elements. And the first question is, what should we aim for? Should we minimize work or should we minimize span? Or try both? I mean, ideally both, but you might have to have a trade-off. And the main goal is to minimize the overall time, so the span, because that's the thing you can't easily get smaller. And as a secondary criterion, we'll minimize work. And often we'll aim for something that's called a work-efficient algorithm. So work-efficient means that the work that your parallel algorithm spends is in the same theta class as the best sequential algorithm. And so we allow a constant factor overhead, but other than that, if we take our parallel algorithm and run it on a single thread, it should not be much slower than what's best possible there. So to wake up and get you started, I'd like to ask you whether that's always possible. We had a phenomenal 87 people vote on the attendance code. So we should have a reasonable number for this question too. So far we're just under 60. Okay, let's do it in 5, 4, 3, 2, 1. So quite a split. When you think about it, it is true. You can always find a work-efficient algorithm, and the answer why is pretty boring. It's because I haven't told you that this work-efficient algorithm should have good span. Work-efficient in isolation just means what's in the definition, namely the same theta class as the best sequential algorithm. So you can always take the best sequential algorithm, whatever it is, and that is a work-efficient algorithm by definition. It's just maybe a really crappy parallel algorithm because it might not use parallelism at all. All right? So okay, maybe kind of a boring way to answer the question. A much more interesting question is, can we always find for a problem an algorithm that has the best possible span that's known and is work efficient? And that's not so clear. And I think there's at least examples where we may not know yet. But I'm also not aware of an impossibility result that would say it's unthinkable. But that's more challenging to get sometimes. But just keep in mind, work efficient in isolation only says what it says, namely same theta class as the best sequential algorithm. Right, you haven't missed much. We were basically recapping and have had one question. The main part of this introduction slide that was missing last time is this theorem, and I didn't want to rush it. So this, if you look at this first time, it might seem like a fairly strange theory. I'm always assuming, by looking at the span and the work, I'm assuming that we have as many processing elements as we want. because span is essentially the time you need if you have an infinite amount of processing elements. And that's very unrealistic. And even something like a linear number of processing elements, one core for every part of the input. Not really. We often have a fairly small number, maybe a dozen cores or a few dozen cores on a beefy server, but certainly not millions. So does that mean that this work in span is not actually answering our question? And it turns out the answer is kind of still useful, because we can convert working span into the actual time on a machine with any number of processors. That's known as Brent's theorem. If we have any algorithm where we know span and we know work, all of this is assuming for a specific input size and so on. So under the usual models, it can be worst case, can be average case. That doesn't matter. But these hold, especially the span, works for an arbitrarily large number of processing elements. Then we can also simulate the same algorithm if we have a given number of processing elements, and the time we achieve is this: the span plus work divided by the number of processors, and without affecting the work. So that's the span that we achieve. Now, the proof is essentially a picture. I mean, that statement already says what you're doing, but let me try to illustrate it a bit in an example. So suppose we have some parallel algorithm, and it runs on many processors, but because I'm not able to draw many so well on one slide, let's say many is 5. So here's the 5 processing elements, the 5 RAM machines. Now in the first time step, so time moves down here. In the first time step, they each do something. Each of these boxes should be one instruction. They might read something from memory or write something or do computation. What exactly it is doesn't matter. Then maybe in the second time step, they do another thing. Let's do a third time step where maybe not everyone is doing something. Only those two are. And then a last time step where they again all do something. And then the program terminates. Now, suppose we want to simulate this on just 3 processors. So I can't do 5 things in parallel, but I can do the first 3 things. So I take the first 3 of those boxes and do those in time step 1. And whatever is left, I do in the next time step, again, moving it just across the processing elements. And once I'm done with that, so notice that this is kind of wasted here. Processing element 3 is just sitting there doing nothing for a time step. Then once I'm done with that, I take the next time step of the algorithm I'm simulating and do the same thing. And again, I'm leaving processing element 3 doing nothing at the end of it. For the blue time step, we actually get by with the same time. It fits on the machines, and I guess you can see what the thing will look like here now. So why is that good enough? If you look at how much time we need, the number of time steps here, that's exactly the span. So we call that here T. That's the number of rounds I have to simulate. Now, how big is one round? Well, at most, as many processors as I'm doing work here. So if I want to know what that is, the number of processing elements on the right, I can take the work and divide it by T. That's the number of processing elements I can use there. So that's my my large number of processors. And here I basically have this P hat divided P, and I have to round up. And if you insert what we know about this, then that's something like this. And I'm doing this for each of these rounds. And if I sum this up, I basically get I overall sum the same work. I haven't done more work than before. And for the span, if I want to determine how many rounds I have to do this, I have at least t, because I might have short rounds like the blue one. And then I have overall w divided p. That comes from this here. If you take that and multiply it again by t, then you get exactly that contribution. And this plus t also eats up the slack that I'm leaving potentially all but one processing element running idle, but it's at most one time step wasted for each of these steps. So here I would have to include the rounding, but in big O that's the same. So I think here the rounding should be there. If you want to spell this out, we would have t times and then w divided t times p rounded up. But we can upper bound this by that thing plus 1. And so you see here again, it's w divided p plus t. And we get another plus t for the rounds where it's much smaller. So I don't know if the calculation was very clear, but the idea from an algorithmic point of view is very simple. If you have an algorithm that runs on many processing elements, but you know the span and work that it needs, you can calculate how much the same algorithm would need if you run it on a PRAM with a smaller given number of processors. And the algorithm would just be schedule round robin, assign the next free processor whenever you need another time step done. So in particular, this theorem means it's enough to analyze work and span because we can compute how long an algorithm would take on any number of processors. And we don't need a separate analysis. Apart from these constant factors that are involved in the theta class here, we don't learn anything more from analyzing it on a specific number of processors. Okay, now we've seen some models. Next step is to also do something on these weird machines. And we'll start with something easy and work our way up towards more interesting algorithms. The first section is essentially boring algorithms, but showing you how far they sometimes take you. And we'll come back to the more interesting algorithms in the context of sorting then. In the next section, we'll look at some simple first parallel algorithms, and we'll look at the string matching problem, which you know from Unit 4. But this time we'll look at it from the parallelization angle. And it will turn out to be a relatively easy problem. And what I want to introduce here is a term that's maybe a bit funny, but people kind of stuck with it. We call problems embarrassingly parallel if they're very easy to parallelize. Slightly more detailed, what we mean by that is the overall problem can, without much effort, essentially immediately be split into many small subtasks. And each of them can be solved independently of each other. And the second part is important. They have to be solvable independently, because that means we can do them in parallel. if there are any dependencies that one task needs the result of another one, then parallelism is tricky. But in an embarrassingly parallel program or a problem, that doesn't happen. The tasks are all nice and independent. And a prototypical example is summing up two matrices. It's maybe not such an exciting operation. Everyone's doing matrix multiplies. That's what machine learning inference is. But if you just sum up two matrices, the sum of a matrix and another matrix is the entry-wise sum. So you can just compute each of the entries in the output separately by taking the respective entries of the input. So that's a prototypical embarrassingly parallel problem, and you can write a simple algorithm for that that just does this loop over the output cells in parallel. In a way, that's almost by definition the best possible case for parallel computation. We haven't talked about independence that much yet, but what else could you speed up other than doing many things all at the same time? And the easiest for that is if they don't have anything to do with each other, and they can just be done one after the other. Now, not all problems are like that. Sorting, in a way, is not really like that. At least we haven't seen any way to easily break it into small problems. There may be parts of sorting that are like this, and we'll come back to that. But if you take the problem as a whole, it's not clear what would be a subproblem of sorting that you can solve independently of the others. And the overall problem is still solved by solving all the small problems. So it's not always that easy. So we have two options now. What do you think is the true part for string matching? I mentioned it's a relatively easy problem, but maybe it's not as easy as matrix summation. Yeah, I think we have roughly the number from before. So let me share the results now, and we'll come back to that. I won't tell you yet. Let's have a look, right? Let's think about it a bit. So first of all, of course, we talked about this problem string matching before in detail. Sorry. I'm back on the slides. Welcome back to the slides too. We'll discuss the question in a second. We talked about string matching in detail. Now, we've seen simple things like the brute force algorithm, but that wasn't really the most effective way to solve the problem. And everything we've seen, in particular things like the Knuth-Morris-Pratt algorithm, they have a somewhat inherently sequential component. They became fast precisely by reusing the comparisons that we've just done. And they were exactly trying what the brute force algorithm did not do well, namely learn from the comparisons that they already done in the past. But in a way, that's exactly what you cannot do in a parallel algorithm. At least having these independent subproblems smells like the opposite. So what can we do? In another way to look at the problem, there is some independent subproblems, namely all the guesses in the terminology of Unit 4, we can try to find for all different positions in the text whether or not there's a match of the pattern. So here we'll look at this formulation where we find all occurrences. That makes it a bit more natural here. So we can take as one subproblem checking each of the guesses. So a simple algorithm that follows that approach would be like this. So the first one is a for loop, and it looks otherwise essentially like our brute force algorithm from Unit 4. But I've added here an in parallel. So that's the way how we program PRAM, the PRAM machines. We can use for loops and say in parallel, and what that means for the machine for running this pseudocode is assign each of the values of I a different processing element and do the loop body in parallel. Okay? It's a slick and short, concise way to do this. There's essentially also languages that do roughly that. You have to pay more attention to details though, but it looks otherwise very similar. So OpenMP is a library for C or C++ where you can use parallelism. It has many pitfalls, but that part is easy. And the rest of the algorithm is like in the brute force method. So for each of those guesses, we have to iterate through all of the positions. And we do all the checks. And if we found a match, then we report it. And at this point, you see, it would be inconvenient to try to now find out the earliest match. So instead, we just report all the matches. So happy? Is that a good algorithm? It's okay from the perspective of span, because instead of spending time linear in the length of the text, which is usually much bigger than the pattern, we just spend time proportional to the pattern, even if we do it simply as in here. And we can actually speed this up further. You'll do this in the tutorials. So instead of doing this simple loop, the way so this code has that span, because each of the iterations of the outer loop still has this inner loop. But you can speed up the inner loop further, at least if you allow certain concurrency on the accesses to memory. But the big problem is the work, because that's much more than what we can do in the sequential setting. So here we have the product of m times the work for each loop times the number of iterations. And that's essentially like the brute force method. Now you could say, forget about work. Span is great. I don't care about work. But remember Brent's theorem. You must care about work, because you're not usually running on millions of processing elements. You're running on a few dozen. So the overall time would really be this plus that divided by your number of processors. And so if the work is almost like the sequential, if the work divided by the number of processors is almost like the sequential running time, you haven't gained anything from parallelizing it. So that algorithm is not that great. At least it's not that great if m is not tiny, right? Now we can do better. We can, instead of doing each guess individually, we can break the text into blocks and use something smarter within the blocks. So that's the first kind of general trick. This kind of blocking technique will come up in other examples. And it's the first non-trivial technique as well to do better. So the important bit is that the blocks are overlapping. Each of those has 2 m characters, not just m. But we start every mth character. So we double cover the entire string. That looks like this. So we take the first 2m. And then we take these 2 and these 2. Right? It looks like a brick wall. all the way through. Now we can discuss why we do that in a second. But then for each of the blocks, we again do things in parallel. But then in each block, we use a fancy method that we've learned about before. We call our KMP algorithm on just the little block of the text and the pattern. And we return whatever that returns. So why do I need these overlapping blocks? For that, maybe I want to make my picture a bit more accurate. I guess there's some boundary conditions at the end, but you have to just fill it up. So the lengths of the blocks are chosen to be 2 times m, twice as long as the pattern. So my pattern should be something like this, roughly that length, half of the black boxes. Now, if I only had this first row of boxes, I wouldn't find the occurrence of this pattern here, because it's not entirely within any of those blocks. But if I double cover everything, no matter where I try to hide my pattern, there is one block where it's contained entirely in the middle, or at least all m characters are covered in one of the blocks. And so one of the calls to KMP must find that occurrence, and so we can report it from there. It has the slight nuisance that if you're not careful with the blocks, you might report a match twice. But if you choose them like here, so that they never overlap in exactly m characters, then it works out. So let's analyze a bit how well this works. First of all, we have to do this loop, the overall loop, n over m times roughly. Within big O, the rounding goes away. And inside of here, how much time do we spend? This is constant time. And this one, now you need to remember what the running time of KMP was. It was, for text of length n and a pattern of length m, the running time of KMP is n plus m, order n plus m. So if our text is length n and the pattern has length m, then that's the running time of KMP. Now, what is n and m in our case? M is the same, but then the text is only how long again? It's one block, 2 times m, right? Yeah. So that's still linear in m. So each of the loop iterations has time m, and how many iterations do I have? N divided m. So the overall running time is linear in the total size of the text, or the overall work. Sorry. For the time, for the span of the problem, we do all of these in parallel. So the span is determined by just one of the loop iterations. So it's just this one. That's what's written there. So is that a good algorithm? I guess here it kind of depends. Well, first of all, for coming back to the question, let me show it again. I guess maybe now you can tell. I mean, embarrassingly parallel means that we don't have to do the fancy KMP trick even. And so we're bound to the simple method from before, where we just do all the checks in parallel. And then that's only really a good algorithm if the text is much, much longer than the pattern. And for the KMP version here, span m is okay if m is small. If m and n are roughly of the same length, then we haven't gained anything. Then the parallel algorithm is not much faster. If n and m are roughly the same, nothing is 1. Okay? But if Question? Okay. Okay. Yeah, so the typical example of pattern of string matching would assume that the pattern is much smaller than the text, but yeah. So what can we say so far about string matching in parallel? The methods I've shown you are fairly simple. Once you know KMP, the code was just a few lines, but these already work reasonably well. I mean, under the assumption that your pattern is not enormously long, but if the pattern is reasonably small compared to the text, they give you a lot of speed up for parallelism. Can you do better? And it turns out you can do better even if the pattern is long, but it becomes a really tricky theoretical question. So there's several barriers that you have to overcome. If you remember what KMP did, it does a pre-processing step on the pattern, and you have to speed that up as well, or parallelize that to be better than theta m span. And also the matching part, when you try to find your occurrences in a block, that has to be sped up and parallelized. And so it turns out this is a theoretical possibility on the PRAM, but the algorithms are, as far as I know, not practically relevant, and a bit beyond the scope of the module. But as in many occasions before, I don't want to leave you with the impression that what we've seen is all there is possible. You can do better, but it's much more complicated, and it's not clear if it gives you a speed up in practice. But that doesn't necessarily stop the question from having a positive answer in the model. So here's just for reference, the state of the art as far as I know. And then it depends on the model again. You can do, instead of m, log m times, so an exponential improvement, if you want to phrase it like that. And if you have this concurrent writes, then you can even speed up things further. But again, this is not part of the exam material. It's just for your curiosity and interest. It's a little early for a break. What do you think? Shall we do the break now? Okay. It is early. That's a short one. There were a few questions. One of them was asking for silence in the room a bit more. I think we managed to get that without my intervention, so that's good. The rest was basically small things on the class tests. Well, the assignment. Haha. Okay, didn't read that yet. Well, short answer is yes, it counts. The class test is overall 15%. You can check units 0 for the details. I'm planning with 7 class tests in total, so you can do the math. And yeah. Yep. Okay. Yes. You take the 7 class tests that we will have in the end, and you take your average. Yeah, I know the class test somehow has just this. I don't know why it has 10. That's the default on Canvas. Take the average of all the class tests and scale it to between 0 and 100. 100 would be everything correct, right? The obvious way. And that's 15% of the overall module mark. Okay, good. Yeah, no, that's important. Okay, I think I explained that. Yeah, should have read that question first. I'm planning with 7 class tests. Okay. There was an attendance code. I'll show it again after this. I have to read that carefully again. I'm not 100% sure how the question's meant. So what I showed, I gave this hint last time about the exam cheat puzzle. It has two parameters, the number of questions and the number of honking bits. In the original version, it was 20 questions and 10 honking bits, but these are two numbers. They don't have, it doesn't have to be one is half of the other. You can pick others. And the hint was just look at smaller numbers than 10 and 20. But the actual assignment should be 20 and 10, right? So that was just a hint for you to get started. The final answer should be for the original question. I don't know if I misunderstood the question. Maybe come and find me after the lecture. Attendance coach. There you go. So YouTube keeps giving me these warnings. If you're home, maybe you can send me a quick confirmation whether or not the live stream works. The recording should not be affected. Okay, thanks for checking. All right, it's about time. Well, a few people are outside, but I guess they'll find their way back eventually. I'll start with some more interesting algorithms. We've seen these embarrassingly parallel methods, and where with simple algorithms we could get some reasonable speed up. But that only gets us so far. So to get to more interesting algorithms, we'll need a little bit of build-up. And so I started with a section where we don't solve an actual problem yet, but we build intermediate stages. In the next subsection, we'll look at some little primitive building blocks for parallel algorithms. that turn out useful in a variety of applications, and we will use them for parallel sorting, but they are more general than that indeed. And so by themselves, the problems that we'll see in the next few slides might look a bit uninteresting or esoteric, but bear with me for a bit. We'll come back to them, and they naturally fit into the problems that we will identify for parallelizing sorting methods. The first of these problems is called the prefix sum problem. And so it's a very simple problem. You're given a list of numbers or an array of numbers, and you're supposed to find all the prefix sums. Well, that's just using the name again, summing up the first I elements for every I. And it's okay if we do this in place. So you could think of it as we start with this array, and we want to end up with that array, where the idea is that every entry here contains now the sum of the entries up to this point, including that point. So the last entry will always contain the sum of the entire array. The first entry will always just be the first entry from before. If we have zeros in the array before, then we'll have a run of the same entry. All right, so that's some simple observations about this problem. Again, forget about for the moment why this is an interesting problem. Just assume we want to solve it. What can we do to solve it? Before we start with parallel algorithms, let's see what is the baseline that we compete against. What's the best sequential method? Yep. And I'm not asking about a complicated algorithm. Essentially, the simple, straightforward solution gives you the running time I'm after here. Let's wait for at least 60, maybe. The votes are trickling in. 3 more, 2 more. Oh, wow, it jumped. Okay, there you go. We had votes for various options. You can actually do this pretty fast. You can do it in linear time, which means that's the time to just read the entire array. Okay, how do you do this? Here's the code. It's a very short code. The main trick is just if you want to find the sum up to including the ith element, if you already have the sum up to including the one before, then there's only one more element that you need to add in. So sequentially, you can do it like this. You iterate over I, and then you just do one summation in each step. You start with just the first 2 elements, then you add one more into the sum of the first 2. That gives you the sum of the first 3, and so on and so forth. So we can do it with n-1 additions and linear time overall. Of course, the problem is that that's maximally data dependent. I always need for the next step in the computation, I need the result of what I've just done. That's the antithesis of parallelization. So that won't work. But we can still take this algorithm as inspiration. And it's insightful, and just gives the easier to draw pictures if we focus on a subproblem, namely summing up the array. Now that sounds like we're reaching problems that are so simple. What can you really do interesting with just summing n numbers? Now, if you look at this from the perspective of what additions are done, if you need to sum n numbers up and all you can do is add 2 numbers at a time, you will always need n-1 additions. No way around it. Each step takes 1 number away. But of course, you can choose which numbers you add up and in what order. And this happens to be a binary tree because it's a binary iteration, a binary operation, and you have 2 things that you add up. So the sequential algorithm corresponds to this kind of tree. We start with the first 2, and then we add in the third, and so on. Yeah, forgive me that I didn't start with 0. I'm offending myself here with not being consistent. But yeah, imagine there's a 0, that's a 1. So that aside, that tree is useful for this algorithm, but it has this maximal height, right? We've seen the same kind of tree as the worst case for binary search trees. Of course, I can do better. If I want to minimize the height, I can use a more balanced tree. And now instead of 1, 2, 3, 4, 5, 6, 7 steps that all have to wait for the previous one, I just have 3, height 3. So can we somehow use that also for the prefix sum problem? It also seems if you want to compute the sum of n numbers in that way, there's no way to get below the height of such a tree. At least unless you can do something else than adding 2 numbers at a time, that's the best you can do. Well, but for the simple problem of just summing things up, you can also write this as a proper algorithm that operates on the tree level by level up. So it first executes all those additions, then those, then those. So the parallel time, the span of that algorithm will be the height of the tree. And you can do the exact same thing for the prefix sum problem by just doing all the trees in parallel. That sounds wilder than it is, but it actually has a nice regular structure. So what we'll do is we do the lowest level of the trees. And if you look at what the lowest levels do, they just add up consecutive elements. So the first step adds up consecutive elements. So every element now contains the sum of itself and its left neighbor. In the next step, you do roughly the same, but you jump by 2. So this guy, for example, now contains the sum of these 2. And each of these, remember, was the sum of the 2 neighbors here. So it turns out that this now contains the sum of these last 4 elements. And the same thing is true for all of the others with a few boundary conditions at the beginning. But every element now contains the sum of the 4 elements before it. And guess what? We just keep going like this by doubling how far we jump back. So here we jump back 4 positions, and then we have summed up 8 elements. And if we do this here, we need 1 more round. And now each of these elements in the last round, after the last round, essentially contains a full binary tree of everything to the left of it. And here's the one example highlighted, but it's true for all of those. That's what I meant by doing all the binary trees in parallel. We're not doing them in parallel in the primitive way. We're not recomputing results that they share. We only recompute the results once. That's what's meant by this. By doing this in these rounds, level by level, you automatically avoid any redundant computation. Okay? I think at the level of these pictures, the algorithm is fairly straightforward to understand. And it's quite clear why it works, because every element exactly shows you what it has summed up. In code, it's a little more annoying because you have to do the computations of the indices, but it's the very same idea. So you can do this. I guess that's maybe It doesn't give this nice animation or this nice picture, but to do this step, I only need the previous round step. So I can each time overwrite the array that I'm using. I don't need to keep the old results around. The old rounds can be overwritten. That's that remark. And here comes, for the first time, a property of the model, of the PRAM model, that is somewhere between a bit idealistic or convenient or an idiosyncrasy of the theory. Call it what you want. That's a part that's not so realistic. So if you wanted to implement this, you would have to do that explicitly. But because we're working on the PRAM, everything works in lockstep. So when I do one round of writing to the array, and then the next round reads elements, I can rely on all the writes going through before any of the reads start. Everything's nicely ordered. I do one step after the other. That's the part where on current architectures, you would have to explicitly synchronize the different threads. If you program with threads in a programming language, they run at different speeds at different times. The operating system is even free to schedule them, like pause any one of them for an indefinite amount of time and then wake it up again. So there you would have to explicitly say, now we'll wait for everyone to write their round results and then continue. What we see increasingly is that this kind of abstraction or this synchronization is done in software as part of the programming framework that you're using. And so it's getting less and less of a problem. But the hardware essentially doesn't support it in exactly that way. Anyways, here's the code. It's the same as before. It's just doing this with proper index arithmetic. Nothing complicated going on other than that. The overall number of rounds is, well, the depth of such a binary tree. So it shouldn't surprise you that there's a logarithm involved. And it turns out to be just log base 2 rounded up is enough. Then you compute the step size that doubles in each step. And here's what we actually do in parallel. So the rounds are sequential. I have to do one round after the other. But in each round across the array, I can work in parallel. And what I do in parallel is just a single addition, and then I write it back. So note that I've split this operation into 2 time steps here. And that's depends a bit how your pseudocode is defined. But this makes it explicit that we first read the old results, compute the new results, and then in the second step, we write the result back to the array. That's my way of making this a bit more explicit. You could maybe you're tempted to write this in one line, but you have to keep in mind that it's actually several steps on any hardware that I know of. Okay, otherwise simple code. And this would run reasonably fast. So how fast exactly? In one round, all these additions here, it's constant time because I'm just doing a bunch of additions and reads and writes. And I do all of this in parallel. So in terms of span, this entire loop is constant time, constant span. And constant times the number of rounds gives you the overall span. We have logarithmic number of rounds. So that's log n span overall. That turns out to be best possible depending on the model, but if you have to sum up n numbers and all you can do is these binary additions, that's the tree argument again. Even if just your task is to compute the sum of the numbers, you can't really be better than that unless your model allows weird operations. But let's look at the work as well. The analysis here is essentially the same. You have constant for each inner loop iteration. But for work, analysis for work is essentially ignoring all in parallels. for these loops at least, that's exactly what happens. Instead of doing them in parallel, we have to sum them up. So this was order 1 work, but order order 1 span, but order n work for each of these rounds. And we have logarithmic being many rounds. So the overall work is order n log n. Remember we said we can do prefix sums sequentially in linear time. So our algorithm is not work efficient. It is still a good algorithm because it's low overhead. It's just a logarithmic factor worse in work. So it might, even for a relatively decent number, a reasonable number of processors, give you a speed up. But at least theoretically, we can ask whether we can do better. So it's overall good. We get a speed up. But the question is, can we do even better? So there's, again, a more tricky algorithm that I'm not going to show, where you can do with twice the span, doubling the span, you can get linear work. I instead want to show you something that has 2 benefits. I mean, it's a tiny bit slower. It's 3 times instead of 2 times. But we ignore constants in much of this module anyways. The good thing is it's a bit simpler, and it's more versatile, but because, again, it uses a blocking trick that is more versatile than this concrete problem. It can be applied in other scenarios as well. So let's have a look at that. The idea is to use what we already know, which is an algorithm that has good span, but slightly too much work. So we want to make use of that algorithm, but apply it to slightly smaller instances and do that in parallel. That's always the idea of this blocking. Try to break things down into slightly smaller subproblems so that you can use the slightly slower algorithm, but do that in parallel so that it overall doesn't hurt. Now, if you just do that and keep repeating the same work, you're not saving the work. So you have to do a slightly smarter thing than that. And that's the problem-specific part. So maybe let me do the example first. And so I'll have to draw that. Let's do a simple example where our array is just all ones. I'll have to draw this a bit nice so it doesn't get too messy. It's not my strength. So suppose we have an array of length 12, and we'll break it into blocks of size 4. That number is basically given in the algorithm. So in our example, we have 12. And now we're using blocks of size log n. So we bunch log n elements together, and here that works out to 4. Oh, that's b. So I'm breaking the array up. Why do I use just ones? Well, if I'm computing the prefix sum, what's the prefix sum of an array that is 1 in every position? It's just the first n integers. So it's nice to check that the example worked out correctly. That's why. But other than that, it's general. If it works for these numbers, it basically works for any other numbers in the same way. Okay, so we broke the problem into blocks. Then for each of the blocks in parallel, we compute the local prefix sums, just in the tiny block. And for that, we use the algorithm we already know. So let's do that first on the example. So I take this as small independent arrays, all filled with ones. If I compute the prefix sums, that's just 1, 2, 3, 4 in all of them. Now, maybe it's good to already note how much time this takes. and we'll have to analyze work and span separately. So we use our we use the fast sequential algorithm for this, not the parallel one at this point. We use the fast sequential algorithm, but do it in parallel for all the blocks. And the sequential algorithm had linear time. So each of these takes order b time. And of course, that's the total span as well for the entire round, because it's run in parallel. But we do n divided b times that in work, because we have to sum for work, we have to sum up over all the blocks. All right, so far so good. Now we use the work inefficient algorithm that we've had before, but not on the entire input, only on the rightmost elements from each block. So I look at this subarray, and I'll draw it in the example just as a really fat array with only 3 entries. But you should think of this only containing that last entry of the small arrays. And I compute the prefix sum of that. So 4, 4, and 4 becomes 4, 8, and 12. So previously was 4, 4, 4. And now it's summed up to that. So how much time does that take? I'm using the parallel but work inefficient algorithm for it. The size of this array is n divided by b, because that's the number of blocks that I have. And remember, the work inefficient algorithm had log n span, but n log n work, not the linear time, linear work. So we have log n prime span and n prime log n prime work. Now if you insert what we know about b is log n. So I could have maybe simplified this here earlier. If we have n divided b times b, that's of course just n. If I have log of n prime, if I insert what I know about n prime, n divided log n, that's log n minus log log n. So that's a lower order term. The asymptotic cost here is the same as log n. Span, not spam. And the interesting thing happens here. If I insert n divided log n here, what I get is that the log just cancels. N divided log n times log, and here again I have technically log divided log n, but this divided log n just becomes a minus log log n. That's the lower order term that is dominated by the rest, or you can upper bound it by the rest. And what's left is a log n down here and a log n up here that we can cancel. So that turns out to be just order n. And that's where the magic happened. We took a work inefficient algorithm, but we applied it to a slightly smaller problem so that the overall work that it does is small enough. That's what the parameter choice comes from. The way I presented this is basically I showed you the final result and said, haha, this fell from the sky, and that's how you do it. But the way you should approach this if you do it to a new problem is you work backwards. You have an algorithm that doesn't quite get the work right. So you can compute how much you have to thin out the problem so that the work is what you want. And here it's a log factor that you have to lose. Okay, we're still not done with the overall problem. We've just computed these intermediate steps. So what you do in the last part is you add to each block the prefix sum of the rightmost elements, and that gives you, you can do this again, you do it in parallel for each block, but you can do it sequentially within a block. So you take this number and add it to the orange number. So here you take that number and you add the orange numbers. In the first block, you don't really do anything. You take that one and add these. And then you get the final prefix sum from before. So why is this correct? These are the prefix sums within the block. All that's missing to the overall prefix sums is the sum of all the elements before it. And that's that green entry, because it was the sum of this block and the sum of this block and the prefix sum of that. It's layers of prefix sums on top of each other. So how much time do we need for that? We again do this sequentially. And we need order B for each block. The length of the block, we just do B additions. So the span is order B. And the work is, by the same calculation as here, is linear. So if we sum this all up, what do we have for span? We have order B, which is order log n, remember? And we have log n and we have log n. So the span is log n. And what do we have for work? Sum that up too. So we have order n, we have order n, we have order n. So n. Linear work. That's spelled out here in a bit nicer as well, but I thought it's nicer just to do it on the example. So overall, we found now an algorithm that has the same span as what we had before, up to constant factors. But we reduced the work to order n, and that's the best sequential algorithm, because we have to read the array. So we found a work-efficient algorithm now as well. And funnily, it uses both of the previously best algorithms, but combines them in a smart way so that it's better than either of those in isolation, right? The algorithm both uses the fast sequential algorithm and the previously fast but not work-efficient parallel algorithm. But by combining them with blocks of the right size, you get the overall improvement. Whenever I present this, I feel it's kind of surprising how this works. You can take two things that are not optimal and you combine them, and then the result is better than either of them. But yeah, the clever choice of the size of the block is what makes this happen. There's one more such parallel primitive that we look at, but that will be much shorter because it's essentially the prefix sums in disguise. But it's one more step towards what we'll need for sorting. So the problem here is called compacting an array. And it has two inputs. It has one array of objects. And it has a bit vector that tells you which of the elements you want to keep, all the ones with a 1. And you're supposed to create an output that consists of just the elements that have a 1 on top, but compacted in an array at consecutive positions. Now, luckily, you don't have to work very hard. You can reuse prefix sums and the clever way of assigning things on the PRAM to solve this with very little code. The way this works is you first call prefix sum on the bit vector. So here I'm making a copy of the bit vector first because we need it later, and remember, prefix sums overwrite their input. But essentially we compute the prefix sums of the bit vectors. Now what does that do? It means For example, the 7 here has an entry above it that's a 1. And if I sum up everything that's up to this point, that's 3. And that's exactly the position in the output array where it should go. So once I've computed the prefix sums, I can use these entries above the elements to know where they should be written to. And so I can do the second part in parallel. For each element in A, I either do nothing, namely if there's a 0 above that element, or I take it and write it to the output to the position that's given by this C, by the prefix sum of all the bit vectors. And that's how I can do compacting. So I'm spending constant effort in each of these inner iterations. Because these are all done in parallel, it's constant span and linear work. That gets too small, I guess. I try to make it a bit bigger. And what we have to add is the cost for the prefix sum. Now, let you do the work. That's the final test if you kept everything in your mind, kept everything in memory. I guess I'll show you the code. The key piece of information is on the slide before that. It's an interesting spread of answers. I'll wait for 60 people again. Okay. There we go. It's a good spread, right? But the majority is right. So to finish off my analysis, I almost gave it away already. What we've just seen about the parallel prefix sum, here it is. You can do it in log n span and linear work. Now the span of this overall thing is dominated by the prefix sum. The rest that comes afterward is essentially nothing, just a constant span. And the work is linear in both parts, so it remains big O of n. So that's the right answer, at least if we use the fancy prefix sum algorithm. So all that's left is puzzling what we have together. And indeed, with the preparation that we've just done now, it's not very hard to get substantially faster sorting algorithms if you have multi-core processors. In the last subsection on parallel algorithms, we'll look at the sorting problem again as an example where immediate tricks to parallelize it don't work. It's not an embarrassingly parallel problem. But with the preparation from these primitives from the previous section, we can get something that is useful in practice and is indeed used, for example, in the Java library. Well, let's start from first principles. We've seen two key sorting algorithms, right? Quicksort and merge sort. So there's other sorting algorithms out there, but these are the efficient ones. So that's the two candidates that we could try to parallelize. Merge sort is a little easier, so we start with that one. Now, first of all, it's a recursive algorithm. It's a divide and conquer method. So whenever you do some recursive calls, these are independent. You can do them in parallel. That will introduce a new piece of pseudocode notation where I'll just write in parallel and then two recursive calls. Again, depends on the actual programming language how to do this, but that's something that is even better supported than these parallel loops. But that doesn't get us so far. So if we only parallelize the left and right recursive calls, we still, at the very last step, we have to merge the first half and the second half of the array into the final output. And that takes linear time. We've seen the merging method in detail back then in Unit 3. Unless we somehow parallelize the merging as well, the best we could hope for is go from time n log n, standard merge sort sequential, to big O of n maybe. But we're stuck with that if we don't parallelize the merging step. So in particular, the method that we've seen there, just to remind you, how did we merge two sorted runs? We started with a pointer at the minimum, and then we compared those two. The smaller one goes to the output, and then that pointer moves one forward. And if that one's smaller now, that goes to the output, moves one forward. That doesn't seem to work well in parallel, because again, it's like for the summing up all the, for the sequential prefix sum, every next step seems to depend on the result of the previous step, so I can't do that independently. So we have to find something else where we do treat elements entirely independently. We can do that by conceptually splitting merging into two steps. What merging does conceptually is two things. It finds for each element where it should go in the merged output. And the second stage is it rearranges the elements so that they end up there. In our sequential algorithm, we do the two things interleaved. We always put one element at its final position and then move on. And we only ever find out where an element goes just before we put it there. But we don't have to do it that way. We can split these two things. So if we look at that in more detail, say we pick some element x in the sorted output, then okay, from this picture that I was always drawing in the sorting unit, x could be somewhere here. And now the question is, where does it go in the sorted output? Where does it go? Well, it goes at the position of its rank, namely the number of elements that are smaller is its position, plus minus 1. How many elements are smaller than x in this run? Well, that's exactly the position in that run, because it's a sorted list. In here, we don't know. We have to search where x goes. But there's some position where x would fall if it was inserted into that run. How do we find that position? Well, we can do a binary search. So the overall position of x in the sorted output is the sum of the number of elements that are smaller than x in the left and in the right run. And 1 we get for free, because it's the position where that element is located. And for the other, we need one binary search in the other run, starting in the middle, and then you've seen it in more detail in Unit 2. So with the binary search, we can find where X needs to go. But then we just do this in parallel for all the elements, save where they should go, and then put them there in the second step. And in code, that looks like this. So let's go through this in a little detail. First of all, the simple part is the parallel recursive calls. So that almost looks like standard merge sort with two small twists. First of all, like in standard merge sort, we find the middle point. That's where we split. We're not doing peak sort, right? Then we can do in parallel the two recursive calls. And remember, we have to pass a buffer around. And the convention was that we use the buffer, but the sorted result at the end is back in the array that the unsorted elements were in. Then we call parallel merge. Well, we'll come to that in a second, which leaves everything in the buffer. So we have to copy it back afterwards. And this last part, this we can do in parallel by a simple loop. I just take every loop iteration, takes one element from one array, copies it into the other one. That we can do in parallel. Now for the merging itself, we first determine the rank of each element. And for that, we do the elements in the left run and the elements in the right run separately. First, we do the ones that are in the left run. So we know how many elements are smaller in their run, and we add the result of a binary search. So here I'm assuming that this binary search returns exactly the number of elements for searching this element in this array. Now the binary search we do sequentially. There's no fancy thing happening parallel-wise. And then we do the same thing again, just the mirror image. We go through all the elements in the right run. We add their rank in the right run, which is just the position, and we do the binary search in the left run. And once you know so here I could have split this up into a second round, but once we have the loop here as well, we can already write them to the buffer array at this point. So how fast is this? Because we don't do the binary search in parallel, it'll have log n, span, and work, exactly. And n is the length of the array. So if we have parallel merge on something of length n half and n half, then we'll have log n span for each binary search. We have constant time for the writes, and we do the rest in parallel. So the overall span of the merge is log n. Now if we analyze the work, we have to do this binary search for each of the elements eventually. So it'll be n log n work. So we're not work efficient, right? Parallel merge needs n log n work, but we could do the standard merge in linear work. But at this point, we'll leave it with that. So we get log n span for the binary search, but the overall work for one merge is n log n. Now, what happens with the recursions is that we start with the entire array, then we recurse on the two halves, and we keep going like this until we have individual elements. We've discussed the recursion for merge sort in more detail back then. The depth of this tree is this log n. That's how many times we have to cut things in half. And on each of these levels, we do things in parallel because the recursive calls are in parallel. But I have to spend at most log n on each step, but actually on the first half rounds down, I have to spend theta log n. So overall, I spend log n times log n span across all the levels. Up to constant factors, it doesn't help that I get smaller inputs. They don't get smaller fast enough. So the total span for this parallel merge sort is log squared. But that's still a substantial speed up from sequential, where we had at least n log n as the running time. So even if you have a reasonable number of processors, this is going to speed up sorting a good bit. Now, we're not work efficient in the merge, which means we also won't be work efficient overall. By essentially the same argument, you also get this extra log factor. You get n log squared n as work for the overall algorithm. But again, as before, a log factor is not that bad. You can still get a good speed up with a reasonable number of processors. Unlike back then, I'll leave it with that, but it is possible to get merge down to work efficient again. There's different solutions. A relatively clean one is not completely dissimilar to our blocking method. But I still decided not to give you the details here because it gets a bit messy. So I'll leave it with a statement that it's possible. And the details are, for example, in the lecture notes from another lecture that are linked on the website if you're curious. Now, what I didn't comment on, both measures are not optimal. The work you can get down to n log n by making the merge work efficient. The span is also not perfect because it's also log squared, and you can't get it down to log n. But that algorithm is even more crazy, so we're not discussing it. But I guess it should be as a comment here. So the combination is possible on the appropriate PRAM model, but the algorithm is substantially more complicated. This part, doable, just a bit too much for us, so I didn't want to do it. This is very tricky. Okay. Let's take a quick look at quicksort before I let you go. We can do the same as before. We can do the recursive calls parallel, easy. Same as before. If we don't parallelize the partition step, we won't really get down below linear time, even in parallel. So that's not going to help us that much. But we can parallelize the partitioning round as well. And we can do this by, again, splitting a recon phase and the data movement phase and doing things in parallel there. Now remember, quicksort partition, you have this pivot element, and for each element you have to find whether it's smaller or larger, and you have to put it to the left or the right. That's the two different parts. Doing all the comparisons with the pivot in parallel is easy. You can just remember the outcome, and then you're done. Moving things to the appropriate place is a little more tricky because the position where an element goes depends on how many other elements are smaller than the pivot. But that's where our friend the prefix sums come again into play. So we can do this as follows. I'll just go over the parallel partition. The code for the overall algorithm is exactly as for standard quicksort, apart from this in parallel here. So we get our pivot element. That's this one, and we swap it to the last position. Then we determine for every element in the array whether it's smaller. So this notation here means, this square brackets means if the condition is true, it's the value 1, otherwise it's 0. It's just a short way to write that. So in S of I, we store a 1 if that element is smaller than the pivot. In L of I, we store the opposite, just to have that convenient. And this we can do in parallel. It's independent, each just compared with the pivot element. Then in parallel, we can do the parallel prefix sums of both S and L. S and L are again just binary arrays. So the prefix sums essentially just count how many ones are before a certain position. And then again in parallel, we write the elements where they should go. So we do the comparison with the pivot again. And then we either use S or we use L to write the element to a certain position in the output. And here again, we make use of the fact that in this PRAM model, these things are synchronized because everything runs in lockstep. So we can just write it to the same array that things come from. We first read all the elements and then we overwrite the array, and the PRAM synchronizes that for us. So that's the details here. First find where elements go and then move them there in the second step. Same as for the merging step. That's the key that we had to split to parallelize things. Because we use the parallel prefix sum, we inherit the logarithmic span. What we can get this time, though, is linear work. So we get an overall algorithm with n log n work without any tricks that I didn't show you. So it's work efficient overall, at least in expectation. And the same span as for merge sort. We have logarithmic span for each partitioning step. And in expectation, we have log many levels in the recursion tree. And so that multiplies again to log squared n. Let me just finish with what I already mentioned. You can get this more sophisticated method that's work efficient n log n span on the crew PRAM at least. But that algorithm is not very practical. If you want to put this in practice, you have to work on reasonable chunks of the subproblem. Otherwise, the synchronization is too much overhead. And you can see some examples of that in the Java library. There's arrays.sort, which is a standard sorting method, but they also have arrays.parallel sort. And they're essentially using the merge sort I've shown you, with a few extra tricks to avoid too small blocks of things. But this is basically based on that. I'll leave it with that. So you've seen a few more sophisticated parallel algorithms. You often get away with much simpler tricks. Many problems are either hard to parallelize or they're embarrassingly parallel. And there's a few in between that you can leave for the experts if you want, or you can have fun with them if you enjoy it. But the embarrassingly parallel problems often give you the most of the benefit. So knowing a few very simple tricks often gets you quite a good way there. Okay, see you in a few hours in our lovely South Campus venue. You're welcome. And if you have questions, please come up.